Okay, so hello and welcome everyone to the third week of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. The course is being instructed by Professor Amaresh Dalal from IIT Guwahati. My name is Debjit. I am a PhD scholar in IIT Madras and I'll be the TA for this course. So, like every week, we will be solving some sample problems together. This week, our topic was the finite difference approximations of different partial differential equations, which is a very crucial step in CFD. Moving forward, we try to solve those discretized equations using different numerical methods. But this initial discretization of you know, the governing equations of any system are partial differential equations, which can't be directly solved by a digital computer. In order to do that, we need to convert them into algebraic equations first. So these discretization techniques takes care of that very important step. And without any further ado, let's jump into the questions from today's session. And if you have any doubts down the way or anything you want to discuss, the floor is open. Okay, so here's the first question of today's session. So it's a match the following type of question. There are two columns and three options each. You have to match each other with the match each other appropriately and find the correct combination from the options given below. So once you figure out the solution, you can put in your response in the poll or you can unmute and answer as well. Uh, let's have an open discussion. So the first column, there are the three different strategies of uh, finite difference approximation. There are forward difference approximation, backward difference approximation, and central difference approximation. And on the second column, we have different mathematical forms which correspond to each of the different types of these strategies. So the first one is fi plus 1 minus fi minus 1 over 2 delta x. The second option is fi plus 1 minus fi over delta x. And the third option is fi minus fi minus 1 over delta x. So which would it be? Would it be option A, A3, B1, C2, or option B, A2, B1, C3, or option C, A1, B2, C3, or option D, A2, B3, C1? Take your time, there is no hurry. Once you have figured out the solution, you can either type in the chat box or unmute yourself and answer. So I'll read out the question once again. The first column has three options A, B, C. A is forward difference approximation, B is backward difference approximation, C is central difference approximation. And on the second column, we have fi plus 1 minus fi minus 1 divided by 2 delta x. Option 2, we have fi plus 1 minus fi divided by delta x. Option 3, we have fi minus fi minus 1 divided by delta x. And among the combinations, we have A3, B1, C2, option A. Then in option B, we have A2, B1, C3. Option C, we have A1, B2, C3. And option D, we have A2, B3, C1. It's a very simple question. So I hope all of you get this right. We have one response in the chat box in favor of option D, A2, B3, C1. Anyone else would like to say anything? So this is the first question of today's session. So it's a match the following type of question. There are three options in each in the two columns. So basically we have different approximation techniques which we use in finite difference method. And you have to match them with the correct mathematical form in the right hand side. So let's start solving it. So for the first one, forward difference, or let's do it the other way around. We will look into the second column and figure out which one is which. So this first option, this fi plus 1 minus fi minus 1 divided by 2 delta x. Which scheme is it? Is it forward, backward, or central?
Central.
Central. Okay, so we have another answer in the chat box in favor of option A. Okay, so A and D are the two answers. Let's see. So this second one, fi plus 1 minus fi over delta x. Which one is it? Is it forward, backward? Central we already have covered.
This is forward.
This is forward. So basically, we have 3 points like this. Our focus point is this I, and we have I plus 1 and I minus 1. So if we are taking 2 points from either side or more, it's basically using a central scheme. If we go forward from I to I plus 1 and use that point, that's a forward difference scheme. And the last one is backward by elimination. So and here we use 1 point behind it, so I and I minus 1. So now let's match them correctly. So A forward difference belongs to 2, backward is 3, and central is 1. So A2, B3, C1. Option D would be the correct answer. So let's look into the solution, and indeed option D is the correct answer. Okay. I hope there are no doubts regarding this one, but anyway, if you have any, never hesitate to ask. The reason for these sessions is to interact as much as possible. Okay, moving on, we'll move on to question number 2 of today's session, which is asking us to choose the statement which correctly describes the Lax equivalence theorem. So this is a very important theorem in CFD, and there are a few statements given in the options below. You have to pick which one is the correct one, which describes Lax equivalence theorem, or in some way is tells what Lax equivalence theorem tells us. So the option A is if
Option B.
okay. So if the option A is if a solution scheme is convergent and stable, it will be consistent. Option B is if a solution scheme is stable and consistent, it will be convergent. And option C is if a solution scheme is convergent and consistent, it will be stable. So, uh, and option D is none of the above. So, option D says none of these are correct. So, which one would it be? So, someone had an answer. I couldn't get you. Can you repeat?
Option B.
Option B. Okay.
Solution is stable and consistent.
Okay. So, we have one response in favor of option B. Let's see what others have to say. Once you figure out the solution, you can unmute and answer. You can put in your solution in the chat box as well. So we have another answer in favor of option B as well. Anyone else would like to say something? So we're focusing on Lax equivalence theorem, and we have to choose a statement which correctly describes that theorem. So statement 1 is if a solution scheme is convergent and stable, it will be consistent. Option B is if it's stable and consistent, then it will be convergent. Option C is if it's convergent and consistent, then it will be stable, or none of the above. So we have two responses in favor of option B. Any other responses? So you have to choose the statement which correctly describes Lax equivalence theorem. Option A is if a solution scheme is convergent and stable, then it will be consistent. Option B, if a solution scheme is stable and consistent, then it will be convergent. Or if it's convergent and consistent, then it will be stable, or none of the above. Okay, so let's have a look at the solution. And the correct solution is indeed option B. So let's go through each term one by one. Okay, give me a second. Yeah, sorry. So let's go through each of the terms one by one. What do they mean? Convergent, we have stable, and we have consistent. So let's begin with this one. What does consistent mean? Anyone?
Same value nearly coming, I think.
Sorry, can you elaborate? Same value as
Uh, same va- Same value is coming every time if each iteration after consistent means.
yeah, consistent does mean that, but in context of CFD, what we talk about consistency is, so we begin with PDEs and then we discretize them and move on to finite difference equations. So the formal way of defining consistency in CFD schemes goes like this. So if I take an FDE, then put these delta x, delta y, delta z, delta t, whatever dimension we are discretizing along, and we put a limit that all of them they tend to zero. Then what happens to these FDEs or finite difference equations? Do they go back to the original PDEs we started from, or don't they? So if they do, then those equations are called consistent. Okay. So there are in fact some equations which there are some schemes which were proposed and used earlier which were not consistent. We will look into these examples as we move along. So as per the lectures, I guess we have lectures till lecture videos till week 5, right? Okay. Anyway, so this is what consistence means. Does that make things clear? Okay. So moving on, there is another term called stable. What does stable mean? Stability of a numerical scheme. What does it mean in context of CFD? So consistence means we will get the same value for PDEs and FDEs as these spacings in the three coordinates x, y, z, and in time as well. If we put a limit that as they go to zero, what happens to those finite difference equations? Do they go back to the original PDEs or not? So if they do, then they will give the same values, and that's how we can call that those are consistent. What about stability now? What does stability of a numerical scheme means? Any guesses, anyone? We hear this term, right? Stable, unstable. In many engineering systems, let's say in mechanics, we learned that if we have a, you know, uh, surface like this, and if we put a ball like this, and then if we have a cup like this and we put a ball in this configuration, then one is stable and one is unstable. So this one is stable and this one is unstable. So this is what it means in context of classical mechanics. But if we come to numerical schemes, what does stability mean then?
Answer is like stable value is, I think exact value is coming same every time is accurate.
Right. So then,
Nearly
yeah.
it's approaching to find.
Yeah. Sorry, I couldn't hear what you were saying. Please carry on. I don't mean to interrupt you.
I'm saying that the solution is approaching to that final value.
Hmm.
So that value is not changing at every time. Same value near to that we are getting.
Yeah. So we are nearing towards the solution value. So what that means is that we start with a guess value which is different from the solution value. So there is a difference. That difference we call error. So we have some error, and basically iteratively we try to solve for the whatever problem that we're trying to approach. And while we're doing that, the error should go down at with each step, with each iteration. So if the error does go down and stay bounded, then that scheme is a stable scheme. In some schemes we will see that this error may go up with time. It may increase with time. It's okay for the error to increase for a few steps and then come back again. But if it uh, repeatedly goes up, if it consistently goes up, I don't want to include this jargon here, but if the error keeps on increasing and goes unbounded, then that kind of a solution, that kind of a scheme is called a stable scheme. And as it comes to the final term, which is convergent, which means that whatever scheme we are using, that approaches the so we are using a numerical scheme, and there could be an analytical solution to whatever problem we are approaching. Not analytical, sorry, an exact solution to the problem. So the numerical solution that we get using the scheme, that should approach the exact solution. And any schemes which enable this are known as convergent schemes. So what Lack's equivalence theorem tells us is that, okay, first of all, beforehand, when we try out a scheme, we won't know whether it's convergent or not. So knowing that beforehand, there this theorem comes into play. It says that if it's stable and the scheme is consistent, then it has to be convergent. So these are things that we can test. We can test whether the scheme is consistent by simply using the FDs, putting a limit, and then checking whether they're matching with the PDs or not. So if they do, then it's consistent. And stability we can check by looking at how the errors are growing, and uh, before even trying out the scheme, there are several ways in which stability can be checked. So one such method we will look into this lecture series is known as von Neumann stability analysis. This we will learn during the future lectures. But this is an analysis which we can do beforehand and then tell that this scheme is stable or this scheme is unstable, or some schemes are unconditionally stable and unconditionally or conditionally stable. There could be some very specific range of values where they are stable and in other regions where they are unstable. So these are details which we will look into later. But what I want to emphasize is that stability can also be determined beforehand. And once we know these two are true, we can be sure that a scheme that we're using will be convergent or not. So this is where this theorem comes in handy. we don't have to always try things out and find out, our solution is diverging, and then go back and change the scheme and all. So this theorem gives us an indication beforehand whether a scheme we're using would be convergent or not. Right? Any questions so far?
Generally, we see residual like values or any other for seeing converging or not. So we'll see residual value.
Hmm. Yeah, that can be done, but you can determine this even without taking a run and looking at the residuals. We can do beforehand. We can check whether it's stable using different stability analysis techniques, and we can check if it's consistent by simply checking the FDs by putting a limit onto them. So before touching a computer, pressing any button, run, we can beforehand, while we're deciding on a scheme, we can determine whether it's stable and consistent or not. So if those are true, then it has to be convergent according to Lax equivalence theorem. What you're saying
Okay.
is true. We can always take a attempt at it and then see whether residuals are going down or not, and then decide on whether to keep on using the scheme or change. But this theorem can tell you beforehand without even taking the run. So what happens is now computational cost is very cheap, right? So that's why uh, it's okay to take a run and then check. It's okay to go by trial and error. But earlier, when computational cost was very high, then we could not afford to, try once and then, fail, go back, try again, and going by trial and error was a costly affair. Was a costly affair. So that's where this theorem
Okay, okay, I
comes in.
got.
Okay. Anything else? Anyone? If you have anything, any clarification that you require or anything to discuss regarding these questions, regarding something else, regarding the lectures, uh, please don't hesitate to reach out. Okay. All right. So we will move along. We'll move on to question number 3 of today's session. So I have these different symbols P, F, N, R, and D, which mean different things. So P means exact solution of PDE, F means exact solution of an FDE, N means numerical solution of FDE from a real computer with finite accuracy. R means a round off error, and D means a discretization error. So these are the meanings of these 5 symbols. And now I have 4 options given here. You have to pick out the incorrect option. So there are 3 correct options and 1 incorrect one. So the first option is R equal to N minus F, D equal to P minus F, C is R plus P equal to D plus N, D is R minus P equal to D minus N. There is one equation here which is wrong, which does not hold up. So you have to find out which one is that. So once you have figured it out, put in your response in the chat box, or you can unmute and answer as well. There is no hurry. Try to do this correctly. It may be a bit confusing. So first of all, let's familiarize with the different terms. So P is the exact solution of the PDE. So we have a PDE, and the exact solution of it would be P. And F would be the exact solution of an FDE. So FDEs can be solved by not using a computer as well. So it's that exact solution. And N is the numerical solution where a computer has been used to solve those finite difference equations. And once we involve a computer into the picture, then it comes with a finite accuracy. It introduces some kinds of errors. R is the round of error, which is the kind of error which comes from finite accuracy, and D is a discretization error. Okay, so we have one response in the chat box which says option D. Let's see what others have to say. Okay, another response in favor of option D. Okay, let's see. Let's see what others have to say. There is no hurry. Take your time. Try to see which one is correct and incorrect. We need to find out the incorrect one. So we have five variables here. P means exact solution of PDE. F means exact solution of FDE, which is a finite difference equation. N means numerical solution of a finite difference equation from a real computer with finite accuracy. R is the round off error, and D is the discretization error. And we have four options, one of which is incorrect. The four options are R equal to N minus F, B D equal to P minus F, R plus P equal to D plus N, and R minus P equal to D minus N. Alright, so we have another response in favor of option B. So option B has one response and D has two. Let's see what others have to say. If any part of the question is unclear or if you would like to discuss anything, please unmute and go ahead. All right, so let's have a look at the solution. So the solution is indeed option D. Okay, we received another in favor of option C. So if I go back, so this was the response distribution here, and indeed D is the correct answer, which two of you figured out correctly. So let's go option by option. So R equal to N minus F. R is what? The round of error, which comes from using a computer to solve the FDs uh, due to a finite accuracy or a rounding of different numbers. So here this would be equal to N minus F, where F is the exact solution and N is whatever numerical solution we got. So option A is a correct option. So regarding this, I would like to say about this finite accuracy thing. Earlier we had 16-bit devices, then we moved on to 32-bit computers, and now most computers are 64-bit. At least the one that I'm using right now is a 64-bit one, and uh, I guess the one that you are using are also 64-bit. So, or at least 32-bit. So what these mean is that we can go up to a certain number of digits for saving one number. So let's say there is some 3.0000016. So due to limitations of the device, we may have to cut off this 16 and work with the remaining part. So this is where this round of error comes into picture, and it keeps adding up as we you know go forward using our algorithms. So round of error equal to the numerical solution minus the exact solution of the FT is n minus f. Option A is correct. Then if we come to the second option, option B, D equal to P minus F. D is the discretization error, or another name of this is truncation error. So this is the error which comes as a result of, as we saw. So while discretizing, we leave out some higher order terms and deal with uh, only a few lower order terms only, which are of higher magnitude. So this is where discretization error comes in, and this is the difference between the exact solution minus the exact solution of a PDE minus the exact solution of an FDE. So if we hadn't done that truncation, then we would have gotten the exact solution of the original PDE. So that would have been the original case. But since we're not doing that, we're discretizing and leaving out some terms, we're truncating them. So that's where this error comes in. So D equal to P minus F. Option B is also correct. Now option C is a bit tricky one. So here, what you can do is consider these as equation one and equation two, and then uh, take a difference between them. So we will have R minus D equal to N minus P, and with a little bit of rearrangement, we can get R plus P equal to D plus N. So that's how option C is also correct. And as we can see, option D has to be wrong because it does not match up with this one. It's not consistent with this one, with this equation, which we know to be true. So that's why this is an incorrect statement, but the correct option, since we have to choose the incorrect option, right? So that's why option D would have been the correct answer. So any questions, anyone? Anything you would like to add? Yeah.
Yeah, if we go for higher order,
Hmm.
then accuracy will increase or decrease. Just
As far as your discretization error is concerned, it will go down. So that's why, you know, using higher order schemes. Let's say we have a scheme which has a order of accuracy of delta x, and we have another scheme which has delta x square. So this second order one would definitely have much less discretization error. So that's why higher order schemes are preferred. But the downside to that is the equations get a bit more complicated. We have to deal with more terms and more data points at a particular uh, point of calculation. So we saw this, right? So in central difference scheme, uh,
okay.
yeah. So if we are using a central difference scheme, using, let's say, okay, central difference, or shall we take another example? So let's say we are using a forward difference scheme, and the first order one would look something like this, and if we go to a second order one, then it would look something like this. So I plus one. I hope I did this correctly, but anyway. So it will be 2 delta x. So this one is second order and this one is first order. We do see that this one is better. The second order scheme does prove better. But the added complexity is that during each calculation you have to know the three terms, and for this one you have to deal with only two terms. So it adds a bit of complicacy, but gives better results, reduces the discretization error. Okay.
Okay.
Okay. Anything else? Anyone? No, right? Okay. So we will move on. We'll move on to question number 4. So what is the order of accuracy for forward difference approximation of a second order derivative? Is it option A 2, option B 1, option C 0, or option D insufficient data? So we are looking at a forward difference approximation of a second order derivative, something like this. Okay, we have one answer in favor of option A. Let's see what others have to say. Okay, so the last equation I wrote a bit wrong. I'll correct that. To try to figure out this one first, I'll clarify. Two responses in favor of option A. A has two takers. Let's see what others have to say. If they pick any other answer or not. So what is the order of accuracy for forward difference approximation of second order derivative? Is it option A 2, is it option B 1, option C 0, or option D insufficient data? We have another response in favor of option A. So three people in favor of option A. Any other option takers? Anyone? Okay, so everyone seems to be happy with option A, but the correct answer is insufficient data because I haven't mentioned the number of terms that you are using for a forward difference approximation. So let's say you want to do a second order derivative and 1 second. So yeah, so as we saw earlier in one of the examples that I gave, that we can write the second order derivative in this way for using a forward difference scheme. That is this two? Is there a two or is it just delta x cube square? I think there is no two. Yeah, there is no two there. So this is what we can do using 3 points. What if I did this? So I'll discretize it like this. So alpha I plus 3 plus beta I plus 2 plus gamma I plus 1 plus some delta, or we won't use delta. Let's say I use mu into fi. So here I am using 4 points. This one would have an order of accuracy delta x squared. So 2 and option A would have been correct. But if I had used more points, then it could be potentially have a higher order of accuracy. Right? Am I making my point clear that since the number of points are not mentioned that we are using for a given calculation, the order of accuracy cannot be determined. So the question does not have sufficient data in order to solve this. Am I making sense?
Minimum order, we will get to second order accuracy.
Yeah, that's true. That's the minimum one, but it could be more, right?
Yeah, it could be more, but two will be okay. No?
2 will be okay. So it might be okay for you, it might not be okay with me. It really depends on what our definition of okay is. Isn't that so? So my point is you can use more grid points and get a higher order of accuracy and reduce your truncation error, but that will come with the added you know the added complexity of using more points and figuring out a correct discretization scheme for it. But otherwise, we are good to go. Any questions on this? Okay, so here I have this alpha, beta, gamma, mu, and so on. So how can we figure this out? Let's say I want to make a scheme like this. So how do I determine alpha, beta, gamma, and mu, all these coefficients? I have taken them randomly, right? But I don't know their value. They would be some, 1 by 7, 3 by 6, or not 3 by 6, 5 by 6, or some number. How to figure out that number? What are the two ways that we learned in the video lectures? So one way is by Taylor series expansion. So what I do here is I simply take this double derivative. No, sorry. I take, uh, sorry. So I take, any value at say I plus 3 over here. Uh, okay. And then I'll expand it out in a Taylor series form where fi delta x into, dou fi dou x plus delta square by 2 factorial delta del 2 fi rho x and so on. And this same thing I can do for all these terms and then mathematically solve for these alpha, beta, gamma, and mu. And there is a second way as well. So this was the first way, this Taylor series expansion. And there is a second way as well. What is that? What did we learn? So we learned two different ways of discretizing. One was using Taylor series expansion. What was the second one? That was by using a polynomial form or polynomial expansion. So here what we do is we approximate that this f is some ax is cubed plus bx squared plus cx plus d, some polynomial form we give it. Then this is fi plus 1 will do a similar kind of thing, I plus 2 will do a similar kind of thing. So here it will be x plus h, or not h, I'll write delta x q and so on. So and then using the data then we can figure out these a b c and d, and then once we have those then we can use them to determine something like this. There also we can figure out all these alpha, beta, gamma, and mu, the mathematical values of them, the numbers. Right? So these are the two techniques which we can use to discretize PDEs. Okay. Any questions on this so far? Okay. If there are no questions, we'll move on. We'll move on to question number 5, which is asking us what is the main purpose of using a non-uniform grid? So we learned about structured mesh and so on. So and mostly the mathematical forms that we are dealing with, they are uniformly spaced grids. So there are some non-uniform grids as well where these spacings are different each time. So it could be delta xi plus 1. They may not be equal to each other. So those are called non-uniform grids. Why are they used? Option A, in order to resolve sharp gradients. Option B, in order to get higher order of accuracy. Option C, to ensure convergence. Or is it D, all of the above? The main purpose of using a non-uniform grid. We have one answer in favor of option D, all of the above. Let's see what others have to say. Sorry. What is the main purpose of using a non-uniform grid? Is it option A, to resolve sharp gradients? Is it option B, to get a higher order of accuracy? Is it option C, to ensure convergence? Or is it D, all of the above? We have another answer in favor of option A, to resolve sharp gradients. Any other responses? Anyone? Option A. So we have two responses in favor of option A. Let's have a look at the solution, and it is indeed option A, to resolve sharp gradients. So why is that? So mainly what happens is one very good and very repeated example is the example of the boundary layer. So let's say I have a boundary layer like this over a for flow over a flat plate. So within this boundary layer, there are very high gradients, but somewhere far away from it, there are no gradients at all, or the gradients are very small, and there are these very sharp gradients near the boundary. So if I'm trying to model this, if I'm trying to, using CFD, I'm trying to solve this. So I don't need very close spaced grids in the regions where there is no gradient. But in the region of the gradient, in order to capture that, I need very sharp, uh, a very refined grid. That's the term used. Uh, so this is why a non-uniform grid is necessary in order to resolve the sharp gradients which are locally present, not everywhere. So if my entire domain had sharp gradients, then using a non-uniform grid won't make sense. But you know if there are locally present sharp gradients, then in order to resolve them, a non-uniform grid becomes handy. Because if there were sharp gradients everywhere, let's say we have something like this, we have x and f, and the gradients are like this. So for this, I anyway need a very sharp grid everywhere in order to capture all this. But if it was something like this, that there are very sharp gradients and there are not much action going on for the rest of the domain. So here I'll only use a uh, refined grid in this locality, and then use a more uh, far away spaced grids in the quieter region. Okay, so using these grids, why are they important? So I'll give an example. Let's say I have a curve which is like this. Okay, and let's say this is our domain which goes from x equal to 0 to L. And let's say we use L by 4 as our grid spacing, something like this. Okay, so then if we solve, so we will find this value, we will find this value and this value. So from a CFD solution, it would look something like this. So I have something here, something here, something here, something here, and something here. So if I connect these points, it would look something like this. Does it represent the exact solution, the original one, which is actually happening? So there is a very sharp dip here, which it is essentially missing out. So in order to capture that, the grid points in between are also necessary. So if I now use L by 8 as my grid spacing, now I'm getting these points, then I'll get a point like this, I'll get a point like this, and now if I join them, let me use a different color now. And now if I join the points, it would look something like this, which is a much better representation of the original one, right? So that's why even we need closely spaced grids in order to figure out the correct gradients or correct values. And in such regions, as we showed here, where there are sharp gradients and those gradients are changing as well, those are the regions where we need even closely spaced grids. And that's where non-uniform meshes, they come in handy. There is something called adaptive meshing. Have you heard of it? So people who have some experience in using CFD tools would definitely come across this adaptive mesh. So what are these? What are the use of them? Has anyone come across this? please don't hesitate. I mean, if you have any experience sort of with adaptive mesh using them, or you saw anywhere else, we can have a discussion on it. What are adaptive mesh? Any idea?
It takes shapes of what we volume we have created.
Can
At
you
where
uh,
it takes shapes in a discretized way of that volume we have taken for analysis,
hmm,
and where which are any sharp edges are there,
hmm.
there it will do fine meshes.
Okay, and yeah, so let's say we have a domain like this, a 2D one. So this is X and this is Y, and sorry. So let's say we have a domain like this, and there are, initially some very sharp gradients here and here, and not in the rest of the domain. So with that knowledge, you try to make a mesh which is more, sharp in this region and more sharp in this region, and you leave the rest of the region out to these widely spaced grids. Now, let's say we take a time evolving problem. So this entire thing is a function of time, not only space. So this f is like an x, y, t kind of thing. So with time, let's say in these other regions where you had taken, widely spaced grids, there are also some, some vortices, some gradients they show up. So then these widely spaced grid won't be able to resolve that correctly. So that's where adaptive mesh comes in. This is a strategy in which you look into the uh, current value of gradients and then adapt your mesh to it. So what happens is after some time, let's say when these gradients have appeared, then those regions would be refined as well. So the mesh itself changes with time. So new gradients appearing, I'm adding more grid points in that region. And then, the opposite also occurs. So let's say in this region where you had very sharp gradients initially, that place has quieted down now, quietened down. So then these closely spaced grids are not required. They are increasing your computational cost. Then these are unrefined as well. So this region is again goes back to this wide spacings. So this strategy is known as adaptive meshing. Another name is dynamic meshing. So with time, the mesh changes. That's why they are called dynamic, right? Okay. Any questions on this up until now? Okay, if not, we will move on. We move on to question number 6 of today's session, which is as number of grid points increases, what happens? Option A, round of error decreases. Option B, truncation error increases. Option C, both A and B. Or is it D, none of the above? Okay, so we have two quick responses, one in favor of option A, one in favor of option C. Okay, another one in favor of option B. The crowd is divided. Let's see if anyone picks D. Okay, another in favor of option B. So as the number of grid points increases, what happens to round of error? What happens to truncation error? There is a option A says round of error decreases. Option B says truncation error increases. Option C says both A and B. And option D says none of the above. Okay, now we have one response in favor of option D as well. Great. Another option D. So if it was a question in KBC, कौन बनेगा करोड़पति, and then if the participant took an audience poll, then it would be one hell of a divided poll for this question. Okay, so far we have three responses in favor of D, one in favor of C, two in favor of B, and one in favor of A. Let's look at the correct solution. It is actually option D. So whatever majority, that majority wins. So let's look into this in a bit more detail. So if the grid points, number of grid, the if the mesh becomes more refined, if the number of grid points increases, then what happens to the round of error? So let's say we have a grid point like this, we have a mesh like this, and there are round of errors at each point. So let's say if I double the grid, if I make it like this, if I take 10 points instead of 5, then a round of error gets added. It's accrued at all the additional points as well. So there is a theory which says that this round of error, this is proportional to the number of grid points. So here n is the number of grid points. So if this if this number of grid point increases as told in the question, the round of error would also increase. So option A is incorrect, right? Then what happens to the truncation error? So if I increase the number of grid points, what happens to my delta x? So we had a delta x1 like this, and later on, after increasing the number of grid points, we have a delta x2 like this. So delta x2 is less than delta x1. And as we saw that in truncation error, what happens? So we have some mathematical FDE. So I'll write it down explicitly. Some FDE we have, and then if we put limit x tends to 0, this if it is consistent, then this goes toward an PDE. It represents a better version of the PDE. So the truncation error, which is something like you know the order of delta x to the power n. So delta x is anyway less than 1 and n is a positive number, uh, finite positive number. So if delta x decreases, this entire thing decreases. So this is the truncation error which is related to this. This also decreases. So if I'm increasing my grid points, what is happening to my truncation error? It is decreasing. So this second option is incorrect as well. And both A and B would naturally be incorrect. So none of the above would be the correct answer. Right? Any questions, any clarifications on this? Please come forward. No questions?
No questions. No questions, sir.
Okay. So as you see here, this increasing grid points, if we blindly keep on increasing, then it may not be beneficial. There has to be some optimization between this increasing round of error and decreasing transition error. Now, of course, practically, this round of error is very low for this very advanced, high accuracy computers. So, the increase in round of error, increasing grid points doesn't hurt us much. But there is another very important aspect that we have to take into account. As we increase the grid points, our calculation time increases. We have to make bigger calculations using those increased number of grid points. So that increases our time required, power required by the computer, and if we are looking into the time wasted, or I won't say wasted, time spent behind that calculation, that is a loss in itself. So the number of grid points has to be optimized. We cannot go on blindly increasing it and we hope for more accurate solution. So up to a certain level of accuracy, we have to accept, and we have to limit increasing the grid points up to a certain level, keeping those cost optimizations in mind. Would anyone like to add something?
No, sir.
Okay, so if there are no questions from your side, I'll move on. We'll go on to question number 7 of today's session. So here I've given a fourth order accurate scheme representing a second order derivative, the form shown below. So I have f double prime x equal to a f of x plus 2h. Here h is basically delta x. Okay. So a f of x plus 2h, b f of x plus h, c f of x, d f of x minus h, and e f of x minus 2h divided by 12h squared. So there are some possible candidate numbers for these values of a, b, c, and d in the options given below. You'll have to pick which one seems to be valid. So these a, b, c, and d, these are nothing but coefficients. So and those coefficients, there are different options are given here, so you'll have to pick which one is correct.
Sir, question number 7 is not displayed on my laptop now.
Is that so? What about others? Is it not displaying?
It's visible, sir.
It's visible from my side.
Okay, so for others it is visible, so I hope, sir, it's a problem on your side and not.
No internet problem.
Maybe you can consider rejoining once.
Now it's visible.
Now
Now
it's
it's
visible,
visible.
right? Okay, great. Okay. So this is the equation we have in hand. It's a fourth order accurate scheme for a second order derivative. And we have these coefficients a, b, c, d, and e. And we have some possible candidates as the numbers which are, as the correct values for this a, b, c, and d. So which one would be correct? So option A is -1, 16, -30, 16, comma 1. So this essentially means A equal to -1, B equal to 16, C equal to -30, D equal to 16, and E equal to -1. So I hope this is clear. You know, I didn't explicitly put these equal to signs and the coefficients over here, just the numbers in order. So we have three responses in favor of option A. In favor of option A, we have three responses. Let's see what others have to say. We have a fourth order accurate scheme representing a second order derivative as shown in the formula, and there are 5 coefficients over here in the equation a, b, c, d and e, and we have some possible candidates for the correct values of those coefficients. So pick out the correct combination from the options. Option A, as 3 people have claimed, is -1, 16, -30, 16, -1. Option B is 1, 16, -30, 16, 1. Option C is -1, 16, 30, 16, -1. And option D, -1, -16, 30, -16, -1. Okay, let's have a look at the correct solution. It is indeed option A. So, as most of you have already figured out, the someone said in the chat box. Okay, Vinay Yadav told in the chat box that the way that he landed in the answer is uh, by taking sum equal to 0. So this is something that we see in other discretized equations as well. Let's say, a first order derivative can be something like this. Second order one is something like this. So no matter how you discretize these equations, the coefficients, so let's say here I have alpha and beta. So this alpha equal to 1, beta equal to -1, and their sum is equal to 0. Similarly, here I have 1 minus 2 plus 1, the sum is equal to 0. So there is no law which says that it has to be like this, but this is a simple observation which we make while making different discretizations of equations of different order. So here also we are expecting that a plus b plus c plus d plus e, the sum, it has to be 0. So among these different options, only option A seems to satisfy that criteria. The other ones don't. So this is how we can say that option A seems to be the valid combination for this problem. Okay. Yes.
I have one doubt.
Yes. Like 1 second. My laptop's charge ran out. Yeah. Sorry for that.
I had, yeah, I have doubt that if more than option are sum equal to zero,
Sorry. What more than?
so how two option are sum equal to zero?
Yeah. Right. Great. That's a great
In
question.
option, if we have some,
Yes. Please say. You are saying something. Sorry.
yeah, that's I have doubt if sum equal to zero for more than one option.
Hmm.
So how we will get that correct answer?
Right. So that's how the question is being framed. You have to the one framing the question should avoid such things. Otherwise, you let's say I have another option. So I had something like -1, 16, -30, 16, and -1, and here I have this fi plus 2 plus fi plus 1, fi plus fi minus 1, and here I have f I minus 2 divided by some 12 8 square or so on. So let's say I had given another option like this. Let's say I make this 14 minus 28 plus 14 again minus 1. Does this add up? Okay, no. So if it was 15 instead, right? So for this option, it's becoming plus 30 minus 30. it's ultimately becoming 0. But does that mean that there has to be a discretization scheme which is like this? No, right? So we start from deriving a fourth order accurate scheme which is consistent with the PDEs that we are starting from, and then we arrive at it. Then we get these numbers. But uh, you know any set of numbers which satisfy sum equal to 0 does not mean that it represents a correct scheme. Does that answer your question?
Yeah, yeah, got.
So let's say we'll have a look at something more easier. So let's say uh, let's have a look at this one. So I have something like 1 minus 2 1. If I come in and say that we this has to be fi plus 1, then uh, say 2, then I have 3 fi plus fi minus 1. So this is also 3 minus 3 boils down to 0. But does that mean that this is an accurate scheme for finding out f double prime? No, right? So this is invalid. Similarly, any set of coefficients whose sum is 0 does not mean that that would be a proper a proper scheme for discretizing some partial differential equation. So we start from that. This is just to say that this is a good check. Let's say you are trying to discretize some new equation and you landed up with some coefficients like this. Then it's a quick mental check that you can take a sum and see that if it is 0, then okay, this is something similar to what I have seen earlier, right? Does that answer your query?
Yes, yeah, I got that.
Okay. Anything else? Anyone? Any questions so far?
Sir,
Yeah.
I didn't understand why these solutions are not valid if their sums are equal to zero,
Okay.
and why straightforward you rejecting these
Okay.
terms?
Okay. So let's say I have something like this: dou f by dou x equal to 0. This is the PD which I am starting from. Then I am invoking some first order uh, okay, let's say first order accurate forward differencing scheme. That's what I'm invoking, and I'm saying that this this would be my, so from the PD I went on to this FD. Then I see that here I have some coefficients alpha beta which are equal to 1 and minus 1, and I'm observing that their sum is equal to 0, right? But that does not mean that any alpha, any beta which satisfies sum equal to 0 would give a consistent equation here. So let's say if I took alpha equal to 2, something like this, or instead of 0 here, I have, let's say, something else, some uh, some other function like this, right? So here, let's say I took alpha equal to beta equal to 2. So 2 fi plus 1 minus 2 fi minus 1 divided by delta x equal to g of f. Okay, so this is a valid starting point, right? So here my coefficients are going to 0. So this should satisfy. Now if I take, I check consistency now. So now I'll take limit delta x tends to 0. So here this would give me 2 of dou f dou x equal to g of f. Now this is the equation I got now. This is the equation I started with earlier. Are they matching? This is a simple example I took, but are they matching?
No.
No, right? So this is where this comes into picture. So I cannot take any set of coefficients and claim that since their sum is 0, that is a appropriate scheme. Not like that. I discretize the PDEs and get the FDE, and then from there I try to find out what the coefficients are. That's a mathematical process, but that will give me a unique set of coefficients which are appropriate to that scheme. Uh, am I making sense?
Yes, yes, definitely. It's
Okay. Anything else? Anyone? Okay. So if not, we will move on. We will move on to question number 8 of today's session. So question 8 says, what is the order of accuracy for the mixed derivative dou f, dou x? Okay. So here there will be a small correction. So this mixed derivative dou 2f, dou x, dou y. I missed this 2 over here. So anyway, so what is the order of accuracy for this mixed derivative using central difference technique using the points as shown? So I want to find out the derivative over here at I comma j, and I have all these points. I can use any of them. Now using any of these points given here, or I won't say any, let's say I'll make it a bit easier. I'll tell you that using central difference scheme, these are the points which come into use. These 4 points in the 4 corners. So using them, what is the order of accuracy which I can achieve? Is it option A 1, option B 2, option C 3, or option D none of the above? Remember, I am using a central difference technique. So I have a mixed derivative dou 2f, dou x, dou y. I want to evaluate it at any certain point. We'll call that point I comma j. Now using a central difference technique, using the point shown, what is the order of accuracy that I can achieve? Is it 1? Is it 2? Is it 3? Or is it none of the above? Something else. Could be higher. Okay, so we have one response in favor of option B. So one response in favor of option B. Let's see what others have to say. Question number 8 of today's session is asking us what is the order of accuracy for the mixed derivative dou 2f, dou x, dou y using central difference technique using the points as shown in the figure. Is it option A 1, option B 2, option C 3, or option D none of the above? If you need any clarification regarding the question, you can ask. If any part is not clear or anything. We have a mixed derivative here, which is a bit trickier to handle than derivatives of a single variable. Only one response so far. What about others? What do you think? Please give me a moment. Yeah, sorry for that. Okay, so no more responses. We will look into the correct solution now. Correct solution is option B, 2, which someone said correctly. So this is very similar to using you know, doing a double derivative on a single variable only. So this is actually similar to using a dot to f dot x square, but this uh, mixed derivative brings in a little bit of complicacy, but that's easy to handle. We will see how to do this. So we have something like this. I can write it as dou dou y of dou f dou x evaluated at I comma j. Okay. So I can take a central difference here, and using these 2 points we will get, you know, f of I plus 1 comma j uh, minus f of I minus 1 comma j, and it could be divided by 2 delta x. I can take this out. I'll take this 2 delta x out, and now I'll operate this dou dou y on each of these. So what I have here is essentially dou f dou y at I plus 1 comma j and dou f dou y at I minus 1 comma j. So for calculating this point, I needed this one and this one to calculate the dou f dou x. Now we have a dou f dou y operating on each of these. So if we focus on this for now, for dou f dou y, I can use this point and this point. So similarly, for doing this one, I'll use this point and this point. So I have a 2 delta x already here. And okay, remember doing this central difference scheme, we have order of accuracy delta x squared. And similarly, we will take a central difference here also. So now I'll get fi, okay, this is plus 1. So I plus 1, j plus 1 minus f of I plus 1, j minus 1 divided by 2 delta y. Similarly, here I am evaluating at I minus 1. So it will be f I minus 1 comma j plus 1 minus f I minus 1 j minus 1, and this would be divided by 2 delta y. And doing this gives us a truncation error of delta y square. So we can rearrange this into a better form like this. Let's say dou to f dou x dou y is equal to 1 over 4 delta x, delta y, and this would be f I plus 1, j plus 1, minus I plus 1, j minus 1, minus fi minus 1, j minus 1, plus f of I minus 1, j plus 1. Okay, I've already taken this out, so this division is not required. Anyway. And I have an order of accuracy of delta x square and delta y also squared. So the order of accuracy would be 2, same for both. Okay. Any questions on this? Any doubt? No, right? Okay.
No, no.
So we will move on to question number 9 of today's session, which is which scheme is more suitable for use in boundaries of a solution domain? Is it option A, forward difference scheme? Is it option B, backward difference scheme? Is it option C, central difference scheme? Or is it option D, both A and B? So I have a solution domain like this. There are grid points at the boundary, right? The ones that I'm highlighting. Which kind of a scheme would be more suitable for them? Forward difference, backward difference, central difference? Okay, one response in favor of option D. Okay, option both A and B. Anyone else would like to say anything? Okay, so let's have a look at the solution, and it is indeed both A and B. So I'll go back to my figure here. So as you can see, for evaluating this point, I need to use a forward difference scheme. I can't do central, can't do backward because there is no backward here. Similarly, for this point, I have to do backward only. I can't do forward here because there is no forward. And the same thing goes in the other dimension as well. So for this one, these are not present. So I have to use a scheme which goes inward to the domain. So if I have a domain like this, I have to go inward always. So I'll draw an irregular shape, something like this. So any point I have, in order to calculate gradients, I'll have to go inward. So either forward difference scheme or backward difference can be used. And as far as options are considered, option D, both A and B would be the correct answer. Do you have any question regarding this? Very simple thing, but
No, no, sir.
often it becomes confusing. Like later on, if you try to write codes and try to solve this, you have to deal with the boundary separately, because first of all there is a boundary condition, and secondly you have to use a different scheme. So let's say for the rest of the domain, if you're using a central difference scheme, then for the boundaries you have to treat them differently. So that's why making the codes and algorithms for these kinds of problems becomes a bit tricky. So it's nothing too difficult, only the boundaries has to be given special care. Okay, so we will now move on to the last question of today's session. This is regarding the different, operators which are used in difference equations. So we have four options in the both columns. So the columns on the left hand side, they contain the operators, and in the second column on the right hand side, here we have the mathematical fonts of these uh, shorthand operators. So you have to figure out which one is which, and once you have figured out the correct combination, pick out the correct option given below. Take your time to do this correctly. Okay, so let's try to solve this together. What is this? What is this first operator? E to the power n. What is this known as? Okay, so we have a response in favor of option C. So let's solve this together for sake of completion. So what is this operator known as? There is this displacement operator.
Displacement operator, yes, sir.
Correct. So what it does is it simply moves up a point n times. So if I'm starting with fi on e to the power n, this would move this to I plus n. It would displace n points. So the correct one among the mathematical forms would be this one, option 2. So A2. Then this operator, delta plus, what is this known as?
Forward difference operator.
Forward difference operator. Correct. Very good. So this simply means I will take a difference with the forward point. So if I have delta plus fi, that simply means fi plus 1 minus fi I will do. So that is this option 3. So B3. Then this next one, delta bar. What is this operator known as?
Central difference operator.
Central difference operator. So delta bar of fi simply means the central difference about that point. So as you can see, I had to write so much, and on the other hand, on the left hand side, it's a very shorthand notation. So this is why it's very useful when we're writing down, the uh, discretized schemes for very long equations. This would this would be very handy. We can imagine. Now this one delta square. This is also okay. Sorry. I made a mistake here. So delta bar is fi plus 1 minus fi minus 1. First order central difference kind of thing. And this delta and delta bar both are central difference operators, but their difference is like this. So delta bar means I'll take two neighboring points and do it, but using delta without the bar means I'll take half points from here and there. So 1 point from the right, 1 point from the left, but half points, in between points. So these are points which do not actually exist. These are imaginary points. So I have I plus 1, I minus 1. So this I minus half and I plus half. So why even care about them is that if I do it twice, so if I use the same thing twice, I'll end up getting, so I'll end up getting this uh, central difference equation, which we can see in second order derivatives. So that's why this, okay, so C would be 1 and D would be 4. So A2, B3, C1, D4. Option C seems to be the correct answer, and it indeed is. So any questions from your side? So that ends the questions from my side. Okay. So if there are no questions, we will end today's session over here. So it's been a great interaction with you guys. Thanks a lot. So next week we will meet again. Okay.
Okay, thank you, sir.
Thank you.
Thank you.